If you guys want to kind of gather around, we don't have the two monitors, so you may not be able to see unless you come over this way. And I'd like for you guys to be close so I can point out things and talk to you. I've got an Arduino here. For the sake of the Anderson students, I'll hold it up to the webcam. You guys have probably seen it before. Let's pass it around. Probably most of you have seen an Arduino, but in case you're wondering what that looks like, that's in fact an Arduino Uno. And it's essentially the microcontroller we'll be using. The main difference between a microprocessor and a microcontroller is a microcontroller has extra stuff built into it. It's almost like a computer on a chip. So it includes memory typically, and also includes the ability to talk to the outside world with I/O devices. If you think about your computer, anybody know about the chipset on your computer? You know what that is? Well, the chipset basically allows the processor to talk to all the peripherals. That's basically what it does. And so this processor is an Atmel processor on it. It actually has the ability to interface with the outside world. So it has I/O pins on it, which is something a microprocessor, you could say technically has, but the microprocessor is more for sending logic signals to other circuitry. So anyway, I have created a new presentation. If you've been looking on Blackboard, you will not have seen it until last night when I got it done. I want to mention one thing before I forget it. I do have a writing lecture presentation. I would suggest that before you sit down to write your contrast between the inkjet and the microwave, that you look through these slides. I think they're fairly self-explanatory. Some of you may have seen me go through them in the past. There's also a link here, How to Write and Speak Correctly. This is a really good book. It's just reading it, you can tell it's well written, and the writer has an excellent command of the English language. So I would recommend at least glancing through this. It can help you quite a lot, not only in this class but others. I just noticed I don't have the other learning module on, so let me turn it on. By the way, did you guys think of any projects you might be interested in attempting? Any widgets you want to make that you thought, hey, we could do this in mechatronics? Nothing? Okay. I thought you'd want to make a few minions and take over the world. That'd be a good project. A little out of the scope of the class. And out of our capability too, probably. There we go. Okay, so that should be on now where you can see it. I like to go into the view that you guys have in case I missed something like that. Still I'm missing it. Where is it? There it is. Arduino coding. So this is the next learning module. The first thing we're going to attack in this class is learning how to code the Arduino. If you have already done coding, which I think all of you have in some class, or you've done Arduino coding for fun or projects, we'll go through this fairly quickly. So bear with me if this is kind of boring. All right, so if we open up the presentation, my presentations in this class are not long. They're 8 slides or so usually. We'll go through it. I wonder if I can do a... Well, I don't know what Camtasia would record if I show the notes on one screen and the presentation on the other. So we'll just go through this. Come on. There we go. All right, basic Arduino. And with the Arduino, it's not just about coding. You have to understand how to interface to it as well. So we're going to learn a few things today about, well, some electrical stuff as well as some coding stuff. To me, the best way to learn code, the easiest way, is to look at sample code. That's probably the easiest way to understand the syntax and the various commands that are available. So there are actually several examples in the Arduino IDE. What is that? Well, IDE, I don't remember what it stands for, but it's something development environment. It's just what they call it. You can download the latest Arduino IDE, just do a search for it. And basically it's the program where you will create your code to download to the Arduino. Okay, so I'm going to start that program now so you can see it. I really like the program. It's pretty straightforward and easy to use. The Arduino language is very much like C. So it's pretty easy to pick up if you've done Java or C or anything like that. If you haven't, I'll help you. The other nice thing about this IDE is they have a lot of sample code in it. So if you go to File, Examples, you'll see there's all these categories of example programs. So we'll start off in Basics and look at the program called Blink. Okay, if I bring it up, you'll notice it opens a new window. That's fine. I'll just close the old window. That's the way the IDE works. And all I've done is copy this code and put it into the presentation. So we'll go back to the presentation. Just wanted you to see where I got that from. Pardon me. All right, the first thing to note is comments in the code. Do you got, when you, let me back up. What programming languages have you guys experienced? Anybody? Python? Python? I think you've done some Arduino, haven't you? Okay.
Java, C++, Python.
Okay. Can't remember? That's fair? Java? Okay. Well, all of you should be well prepared to learn this. It's very similar to those languages. The first thing to note, though, in all languages is how important it is to comment your code. Okay? If you guys had controls with me, I really ran you through the ringer over not commenting your code. So there are two types of comments in Arduino code, and it's kind of nice. One you'll see here at the beginning. Well, I guess I'm not in the PowerPoint. There we go. Usually you include a comment section at the very beginning, and a lot of times the way that's done is with this, see the /*? That indicates to the Arduino IDE that you're beginning a comment section, not just one line, but a whole section of comments. And then the */ is the end of that comment section. You can put it anywhere in the code that you want, and basically the IDE will just completely ignore it. Okay? So this is for human beings to read and understand. So here, blink turns on an LED for 1 second, then off for 1 second repeatedly. Okay. Most Arduinos have an onboard LED you can control on these various ones. It is attached to digital pin 13. Oh, why my cursor went off. There we go. What are we interested in? We're interested in the Uno. So, excuse me, where's that Uno? Thank you. So if you look at this really close, you'll notice that there is a light right there on the board. It's a surface mount device. It's a LED that's very small. And it is tied to output 13. If you look on the board, you'll see the silk screen. There's numbers 0 through 13, and then ground, and then A ref. If you got a Arduino there in front of you, you should pick it up and look at it. But the thing marked TX and RX are transmit and receive LEDs that flash when you're talking to the Arduino through serial. And the L is the little lamp that you can control that's hooked to pin 13. So I'll pass it around again so you guys can note that little detail. All right, so what they're saying in the comments is that the term LED_built-in is referencing pin 13 on the Arduino Uno. Okay, it's another way of calling out pin 13. Okay. All right. The next section is a section of code that all Arduino programs have, that is a section that is run once. Okay? And just like in C, the motif here is functions. So everything's a function, and you can call functions and make them run. Okay? So void setup there at the beginning, I can get my cursor back, this bit here, void setup, void is just telling you, it's helping the compiler know whether or not you expect this function to return anything, because this function could be called by some other function or some other code. Void just means this function will not return anything. That's all it means. Okay. So that's why it's there. It's not that this code is void of any reason. Okay, that's not what that means. So setup is a function, and all it does is one thing. Well, let me not get too far ahead of myself. This is a line comment. It's got 2 slashes. So anything with 2 slashes is just a comment. Is just a line's worth of comment. Okay, so this is commented well so that you can understand what's going on. All right, pin mode is a command that defines whether this pin should be input or output. It's being set as output. Okay, see, each I/O pin on the Arduino can be used as an input or an output, but you have to set the mode. Okay, you have to tell it what you want to do, and so that's what this command is doing. Notice some of the syntax while we're here. Cursor keeps disappearing. Just like in C, you have to put a semicolon after commands. Okay, you don't put semicolons after functions. you just put it after commands. Okay? And in the beginning, when you're coding Arduino, if you've never used it and you're a little unsure of the syntax, just go into example files to find what you need, cut the command out, put it in your program, and use it. That's how I'm going to code the first couple of programs that I make, so you can see how that works. It's a simple way to start coding in Arduino and to learn the language very quickly. Okay. All right, so this section runs once. The void setup is a default function that runs at the beginning of the program, because you don't need to set the mode of the pin over and over within your code. Once it's an output, that's done. There are other things you do here, variable initialization, things like that, but we'll get into that a little bit later. This is a section of the code that is actually repeated. The loop function does just what it's called. It loops. It runs over and over and over again. So in this program, we're saying that loop as a function will not return anything. Notice that these brackets, these curly brackets, enclose the function, so that all the code for that function is in those brackets. You have to use those brackets. The first thing that happens, we do a digital write. Now, most of these commands are pretty self-explanatory. The way they're named makes it easy to understand. Digital write means that we're changing the status of a pin, an output pin. Okay? So we're going to digital write pin 13, which is LED built in. That's another name for it. And we're going to write it high. We're going to make it go high. Now, if you don't know this, this processor deals with TTL level signals. What that means is that 0 volts or close to it is considered off, 5 volts or close to it is considered on. Okay? So when you say you turn a pin on, what that means is that pin has a 5 volt signal on it. Okay? In other words, it's set at 5 volts. When you turn it off, it has 0 volts on. Okay? So all they're going to do is basically make pin 13 output 5 volts. Okay? I shouldn't say output, it's really being set at 5 volts. Rats. Keep losing my mouse. Delay 1000. What do you think that means? Really simple. There's even a comment here to tell you. Wait for 1 second. So why would it be 1,000? That's not 1. Because it's in milliseconds, exactly. So it's 1,000 milliseconds, which is a second. Good job. Okay. There's another delay command that has finer resolution than this, if I remember right. I don't think you set the delay. Yeah, there's another command called millis. I think that's what it's called, or micro. I don't remember. We'll encounter it along the way. Digital write, LED built in, low. So this is just turning the LED off, and then wait for another second. Okay? And this just happens over and over. So you can see how the LED is just going to turn on and off and on and off. It's really not all that spectacular. But for the sake of demonstrating this, let's go through and connect to the Arduino and make it happen, shall we? Okay. All right, so when we plug in the Arduino, I'm hoping it'll mess up for us. Then I can show you how to deal with the Arduino when it doesn't want to talk to you. All right, so we've got the IDE. We might want to just download the program. Now, they call it upload. I would call it download to the Arduino, but they call it upload to the Arduino. So whatever you want to call it. The point is we're transferring our program into this processor. It's just this little arrow right here. So we'll just say, go do it. I hope it says it can't find it, because I want to show you something. If it does find it, I'll show it to you anyway. Compiling just means that it's taking this code, which this processor has no clue how to run, and turning the code into something that the processor can understand and actually run. Processors, good. Problem uploading to board, that's what I wanted. Processors, microprocessors, microcontrollers use something called machine language. Okay? Assembly language is very close to machine language. It's a one-to-one, but it's a little bit more readable. Anyway, it's basically strings of zeros and ones. And the zeros and ones in their certain patterns represent certain commands that make the processor do things. Okay, beyond that, I don't really want to go into a lot of detail. It doesn't really matter to us, because the compiler takes care of taking what we understand and making it something the Arduino can understand. So we really don't care beyond that. Although, of course, it is good to note that this, like any other computer, deals with only zeros and ones. All right, let's check. Problem uploading to board. See this guide, troubleshooting for suggestions. We'll probably go do that. Invalid library found. That is a separate, let's see, I've forgotten how to copy this. I think I know what's wrong. This is what usually happens. If you go to Tools And where is it? No, not tools. Yeah, it is tools. No. Where's the port? That's what I'm looking for. It doesn't want me to...
Windows isn't finished installing drivers.
Probably. Most likely.
Yep.
Unidentified device. Searching Windows Update. A lot of things can happen. Down here when it turns orange like this, it's complaining about something. Now sometimes it doesn't matter. Sometimes just try it again and it'll work. So whenever you see an error like this, I always suggest trying it again, regardless of what the error is, because for some reason sometimes it'll simply work. Most of the time the problem is that the port that you've connected to is not the port that the program's trying to talk to. So it's trying to talk to the Arduino through some other port. It's just the wrong USB port, and you just choose a different COM port. About 50% of the time, maybe a little bit more, it seems like the IDE will actually detect the correct port and know where the Arduino is and just talk to it. But sometimes that doesn't happen. Why, I don't know. It is really not happy. You know what? I just realized. I may not have... No, I do have connection. Alright, let's see if we can figure out what's going on. Let's try it again. And it'll probably complain again, because yeah, that looks like a fairly serious error. One thing I do is I just try restarting the program. Sometimes that works too. But let me show you something while we're outside of the IDE. One thing that's really handy to know how to do is to get into, come on, go back. Let's just do it this way. This will be quicker. To get into the device manager. Because in the device manager you can, come on computer, you can tell what the computer can see. So if you right click on computer anywhere, you can find it and say manage. It's actually more than just the device manager that it'll bring up. And this is Windows 7, by the way. Do most of you guys run Windows 7 or Windows 10 or 8, 10?
10.
Okay. Well, you need to find where on your computer you can get to the device manager.
And you can just right click the start menu.
Yeah. This is the way I'm used to doing it. My computer's not very happy with me recording and trying to do something else. This computer's about on its last leg. I use it and sometimes actually sit it on my lap like a laptop, and the bottom cover is loose and you can touch it just the wrong way and the screen goes black. So that doesn't bode well for this device. Okay, anyway, not disk management, device manager is what I want. Under device manager you should be able to go under the ports or USB and see the Arduino. It should be listed there. And that'll give you an idea of which port it's connected to, if it'll do it. I think part of my problem is I'm running so many programs. Oddly enough, Outlook actually takes a decent amount of resources, so I'm going to close it. Okay. I don't care about network adapters, Bluetooth peripheral devices. What I'm interested in is COM ports. So if you look under the ports, COM and LPT, you'll see the Arduino Uno on a port. I'm trying to remember how to get into it and see exactly what the port number is. Yeah, port 3. Port settings you don't have to mess with. But essentially this should be on COM 3. You can see it right there. A lot of times it'll, in many of the computers I've used, it'll show the actual COM port beside this. Let's try restarting the IDE and see what happens. If that doesn't work, we'll go online to Arduino site. The Arduino site is actually really good. I wanted to show you guys one thing there anyway. So while the IDE is opening up, I've included a link. Let me go back. Oh, I was already there. Sorry. Get back into this learning module. If you click on the Arduino command reference, it is a link to the Arduino homepage that has a nice reference document with all of the commands that you can use in the IDE. And it's really handy because you can go, like we've seen the digital write command, for example, you can go and click on it and see all the syntax and how to use it and some details about it. Okay, so it's really good information. So it's one way to figure out what the commands do when you're learning the coding. Alright, let's go back to the IDE and see if it'll talk this time. Tools. Port is still grayed out, and I'm not sure why. So I'll try to upload again, and we'll go to Arduino site with the link they recommended and find out why. I'll also unplug this and plug it back in and see if Windows will maybe take care of our problem. But the device was recognized in Windows. It recognized it as an Arduino Uno, so Windows should have been talking to it just fine. This driver was not successfully installed. It was still talking to it last time. Let's try one more time, since I unplugged it while I was trying to upload. Okay. So let's follow this guide. Arduino Uno CC English Guide Troubleshooting. Okay. I think that was the address. Let's see if I got it right. Okay. It's going to be a long document. Tell you what, why don't we do it this way? I don't want to waste time. I will figure out during the break what's going on. We'll go through the presentation first, because I've actually not seen that error before. And that's one thing that happens with these things very commonly, is you'll come across some unique error you've not seen before, and you've got to figure out what's wrong and make it work again. So when I find out what it is, which probably won't take very long during the break, I'll just show you what's going on, and that'll be one more error you'll know how to fix. Okay, so you understand what it should do, and we'll download programs and demonstrate it later. That's fine. I want to talk a little bit about electronics, because half of what you have to do with the Arduino is coding. Well, a quarter of what you do is coding, a half of what you do is debugging, okay? And then the other quarter or so is interfacing. And so you have to understand some electronics concepts. So the internal LED is just fine, but what if you need more than one LED? What if you want an external LED and you want to drive it? How do you do that? Well, if you take a light-emitting diode, which is just like this little light right here, or any light you have, Anderson students, on any device that's on, you'll see a little light come on. Those are usually, well, 99 times out of 100, those are LEDs. If you want to control an external LED, you can't just hook up the LED to 5 volts, for example. Anybody know what happens when you take a regular LED and you hook it up to a 5-volt supply?
Mm-hmm.
What happens to it?
Tends to burn up.
It gets really bright really quick, and then it's really dark forever. It doesn't work anymore because you burn it up, exactly. LEDs are made to conduct a certain amount of current and at a certain voltage. It has a certain forward voltage. And if you exceed that, well, you conduct too much current and the LED burns out. I've done that many times. When I worked for Grody, you guys know that I was dealing with a lot of LEDs. It's kind of interesting, as you increase the voltage. I've taken a power supply, hooked it up to an LED, and turned it on slowly, basically doing what you see in this figure right down here, slowly but surely turning on the LED by increasing the voltage across the terminals. Eventually it starts to come on, and as soon as it starts to conduct a significant amount of current, you'll see light come out of the LED, but it'll be very dim. And as you continue to turn up the voltage, or the electric potential really, across the diode, very quickly the current will increase and the brightness of the LED will increase as well. And there is a specified level of potential you're supposed to put across it, and at that point it will conduct the amount of current that it's designed to conduct. As you continue to turn it up, it doesn't take a whole lot more voltage for the LED to conduct a whole lot more current. Okay, and what happens is the color goes off a little bit. I've taken a red LED, turned it up until it became more of an orange color, and then it went out. So the color actually varies a little bit too as you turn up the electric potential until it's dead. If you reverse bias a light-emitting diode, you can eventually make it conduct current, but it will break down and it'll be shot as well. LEDs are not designed to conduct in reverse. There are diodes designed to conduct in reverse, and they're called Zener diodes, and they're used a lot for voltage regulation. If we need that, we'll talk about that more later. What you really need to know is that you've got to put the right amount of electric potential across the diode so you get the right amount of current through it. Now, what's the right amount? Well, it depends on the LED. Most of the time, about 20 milliamps is a good place to start. That's kind of the high end of a really cheap LED. It's the low end of a good LED. Okay? The brighter an LED is, the more money it costs typically, and the more current it can conduct. Anyway, so most of the time, you're not going to have some specification that tells you what voltage you should put across the LED. So you could start at a calculation of 10 milliamps if you wanted to. That would be fine. Okay? Now, how would you do that when you have no idea what the voltage should be across the LED? Well, let's just pretend for the moment that we know what the electric potential or voltage should be across the LED. Let's go through the math of how we would size a proper resistor. See, what's happening here, we've got a resistor in series with the LED. What will happen is the electric potential from the source will drop across the resistor so that the potential across the LED is the correct amount for that LED. Does that make sense? It won't be too high that way. Okay? So you have to know what voltage source you're using. You can use a 9-volt source, 5-volt source. Most LEDs have a drop from anywhere from about 0.7 to about 1.5 maybe volts is what they're specified to run at. Anyway, so the key to figuring out what size resistor you need is realizing that the current through the resistor and the diode is actually the same. Does that make sense? You guys have all had an electronics course, right? Okay, so the current flow in amps or milliamps going through the resistor is the exact same amount of current going through the LED. So IR1 equals ILED. The electric potential across resistor 1, will simply be the source, which is from here to here, minus the forward voltage requirement of the LED. See, when you're looking at circuits like this, it's really nice to have them oriented vertically because it's kind of like dropping height. And mechanically, it's easy to understand then. See, so it's like at the top of R1, that's the highest height, that's the highest potential. Okay, as you go through R1, that height or that potential drops. Okay, now if I'm going too slow, let me know. If I'm going too fast, slow me down. All right. So to represent the electric potential across R1, it's just the difference between the source voltage and whatever the LED is supposed to have. Let's pretend for the moment we have the data sheet. We know what the LED should have in terms of its current and its forward voltage. So what VF stands for is forward voltage. Now, from Ohm's law, the voltage across R1 is equal to the current through R1, which is the same thing as the current through the LED, multiplied by the resistance of R1, right? V equals IR, okay? Straightforward. Now, since we have two equations for VR1 that both correctly express the electric potential across the resistor, we can set the two sides equal to each other. So the source voltage minus the forward voltage of the LED is equal to the current through the resistor times the resistance of the resistor. And from this equation we can solve for R1 and what it should be if we know what the forward voltage should be across the LED and what current it should have. Now, that's a little bit difficult to understand. It's like, why are we using a resistor? A resistor seems wasteful, right? Why are we using a resistor? Well, if we don't, we burn up the LED. Now, this resistor is serving as what's called a current limiting resistor. To understand how that works, let's pretend for a moment that we do not have the LED at all. Okay? So we're going to just say, what if there's no LED? Okay, very simple circuit with a battery and a resistor. Simple. Okay? If there's no LED, then the forward voltage across the LED is 0, right? Because this point would be directly connected and would be at ground potential. Okay, because this side is ground and this side of the battery is at higher potential. And Anderson students, I hope the cursor is being recorded. We'll find out here in a minute. My first time doing this. So R1 could be calculated, or the relationship is that the voltage across the source, which is the same as the voltage across R1, divided by the current through R1, is equal to R1. So the current going through the resistor is simply the source voltage divided by R1, just Ohm's law again, simple. Now, if you think about it, what happens, let's say we have a 5-volt power supply. and you think about varying R1. As you increase R1, what happens to the current going through the resistor?
Goes down.
Goes down, exactly. And if we decrease the resistance, then the current goes up. So we could use this. Let's say that we know most LEDs like about 10 to 20 milliamps. So we're going to shoot for the low end and try to give the LED a current of 10 milliamps. Okay. We don't know what the forward voltage should be across the LED. Couldn't we use this and say, well, we know we want 10 milliamps. Let's say we got a source voltage of 5 volts. What should R1 be in that case? You guys have a calculator? Grab your calculators. Let's figure out what R1 should be. So 5 volts. When you divide by 10 milliamps, what are you going to divide by? Are you going to divide by 10?
Yeah, by point, about 1,000, right? No,
100th. So 0.01, because you always need to express the units properly. Voltage, okay, for electric potential. You want current in amps. That way you get resistance in ohms. Does that make sense? So 10 milliamps is the same thing. Here, let me write it. If I write it on the board, Columbus or Anderson can't see it. But basically 0.01. Okay, 0.010 is 10 milliamps. Or is a hundredth of an amp, which is 10 milliamps. So divide 5 by 0.01. What do you get?
500.
500, right? So we need a 500 ohm resistor in order to limit the current through the LED to 10 milliamps. Now when we put the LED in circuit, what's going to happen? Will we really get 10 milliamps through the LED?
No.
We won't. Will we get more or less or the same? Well, we said no. So we'll get more or less?
Yes.
Less, that's right. Because now we've got another voltage drop. Effectively, we've got more resistance. Okay, that's one way to think about it. Since there's more resistance, less current is going to flow because now R1 plus the LED represents an effective larger resistance, so less current is going to flow. Okay. Now once you do that, you can actually use a multimeter, measure the voltage drop across the LED, and look, the voltage drop across the LED, as long as the LED is lit up well enough, is going to be pretty much one number, right? Because this curve for the LED shows you that the diode is not particularly sensitive to the forward voltage, right? So the current can vary widely, but the voltage is going to be pretty much one number. Once you know what that voltage drop is, and you see the LED and you say, well, this is kind of dim, would you decrease the resistance or increase the resistance? Decrease it, right? Make the light turn on brighter because you're giving it more current. And you should still get about the same forward voltage drop. I had to use these principles for a friend of mine. I made her a gift. She's a very artsy type person. Have you guys seen the 3D printed tree ball thing that you put a light in the center of it and it projects shadows on your walls with the lights out so it looks like you're in the middle of a forest? It's kind of cool. I made one of them for her for Christmas and she loved it. Well, my light source, the problem with that is that your light source needs to be very, very small. If you take an incandescent bulb, your light source is actually the entire filament. The entire filament is glowing on and giving off photons. You put something like that in the middle of this ball of sticks, basically, and you're going to get a very diffuse, very washed out pattern on the wall. It'll be out of focus. So you really need a point source. Well, no problem. I went down to O'Reilly's and I found a flashlight that was about, I think, $5. It had 3 very bright LEDs in it. Hacked it apart, took the 3 LEDs, cut the circuit board they were on. It was really interesting. You ever take apart, well, you guys have taken apart the microwave at least, so you've seen the circuit board that's there, and it's got that kind of sort of fiberglass phenolic material for the board. Well, the flashlights you get these days that have fairly high power LEDs have a different material for the circuit board. Anyone ever taken one apart and know what it is? It's aluminum. They use aluminum, so they actually use the aluminum for the circuit board and coat it on either side with a non-conductive layer so they can make a circuit out of it. It's kind of neat. They even make vias through the circuit board that are insulated from the aluminum, which is kind of cool. I didn't know that until I took this one apart. But why do you think they'd use aluminum for the circuit board?
Higher heat.
Yeah, exactly. Get the heat out of the LED. Everyone thinks the LEDs are 100% efficient. They're not. LEDs are getting better and their efficiency is increasing. But for a long time, fluorescent lights, like we have above us, are actually more efficient than LEDs. It's really hard to beat fluorescent lights for efficiency, especially with the modern fluorescent lights that they've got. Anyway, there is one thing to note about fluorescent lights. If anyone gives you a bunch of old fluorescent lamps, the ballast in them are probably magnetic ballasts. Magnetic? Yeah, magnetic ballast. Over time, they can degrade and they can eventually cause a fire. My neighbor had a fire in his barn because he used a bunch of them and left them on, and the ballast went bad. And what happens is they get hot, and there's some tar substance inside them that will leak out, and it'll leak out basically on fire. So this was years ago, I was working with him in his barn the other day, helping him out. He's an elderly guy. And I looked up and I noticed there were beams scabbed on to these beams that had been burned. And I was like, what happened here? What's this story? He said, well, fluorescent lights. The ballast caught on fire, and this is what happens. You can mitigate the problem with about $20 investment. There are electronic ballasts that won't do that. So if you get some old fluorescent lights and you're thinking of putting them up in your garage like I've got right now, you might want to get some electronic ballast. That's one thing on my to-do list. So I don't leave my lights on in my garage because I don't trust them. Anyway, does this make sense? Okay, do you think you could size a resistor for an LED? Okay. All right, so that's how we could hook up external LEDs, and once I get the Arduino to talk, I'll actually do that for you. I'll grab some breadboard and we'll hook up some resistors and LEDs and make a program to let the Arduino drive them. Outputs are not enough. We also would like some inputs. Now, most of the time, the types of switches you'll use with the Arduino are called single pole, single throw, SPST. Okay? There are other types of switches, but this is the most common type. They're basically either break, open, or make, closed. Okay? That's all they are. Now, if you just hook up a switch to the input and you don't have this resistor here, R1, then you can make that pin go to 5 volts by closing the switch. But when you open the switch, what's the voltage on the pin? Don't know. It's just floating, right? It's undefined. It turns out that the resistance of this input is actually high enough. Charge can sit here even once you open up the switch and make that pin remain on, because the electric potential is still 5 volts. Okay? So you need something with a switch like this in order to make the pin go to the opposite state. So what's used here is a resistor. Now this resistor is a fairly low resistance, and what it does, since this side going to positive is a very high resistance, then this point is fairly close to ground. Do you guys remember voltage dividers from your classes? The concept of a voltage divider is actually very useful. It doesn't seem like it in the ECET class we have you take. You just get a resistor, get a voltage, use Ohm's law, figure out the voltage in between the two resistors once you have them in a line. Seems very useless. Actually, we're going to use the concept of a voltage divider over and over in this class. And this is one place. Because, see, this Arduino is connected, ultimately, to positive 5 volts. And so that completes a circuit here where essentially the Arduino acts like a very large input resistance or input impedance. And this is a very small resistance or impedance, and so this point is fairly close to ground. Okay? We've got a picture on the next few slides of voltage divider, so this will become more clear. But right now, think of it this way. When the switch is closed, current will flow from 5 volts directly down to ground through this 220 ohm resistor. But it will also flow into this input pin, and essentially this input pin will be at 5 volts. Does that make sense? Anyone know what this is called? What kind of term we give this resistor? Last time we had a current limiting resistor for the LED. Now we've got a pull-down resistor. That's it. There are also, and why is it called pull-down? Well, it's because it's pulling this pin close to ground. It has a fairly low resistance, and it tries to make this pin be close to ground potential, which is off. Okay. There are also other types of resistors called pull-up resistors. If you imagine just switching this switch with the resistor, just flipping places, then when the switch closes, it would be down here, and it would connect this point to ground. That would make the input off. But when you open the switch, then the resistor, which would be in this position, would connect the pin to positive 5 volts. You see how that inverts the logic? So that basically when you're pressing the switch, as it is in this case, the pin goes high. But if you trade positions of the switch and the resistor, and you press the switch, then it makes the pin go low. You see? So there are pull-up resistors and pull-down resistors. How do you size a pull-up or pull-down resistor? Well, it depends on the input impedance here. Okay, for the Arduino, this is a really low resistance. See, what's going to happen whenever you close this switch is a significant quantity of current is going to flow straight to ground, heating up the resistor and doing nothing useful. Okay, in fact, grab your calculators. What would the current flow be? Once this switch is closed, neglect this side, what would the current flow be to ground through R1 at 220 ohms? Assuming 5 volts. Everybody get 23 milliamps about? Okay. Is that a lot of current? No, but will it drain a battery that doesn't have a lot to give? Yeah. So it would be better to use a higher resistance. Now, if I remember right, about 10K is reasonable. What if we put a 10K in? Now what would our current be? You don't need your calculator for this. Move the decimal place over 4 times and you got it. All right? A half of a milliamp is what it would be. That's a whole lot better when you're running off of batteries. Mr. Schottler's probably bored because I'm sure your dad has drilled all this into you over and over again. Electrical engineer father, so. Does that make sense? The difference between a pull-up, pull-down, and a current limiting resistor. Okay. There's something to know about mechanical switches, however, something called switch bounce. Has anyone ever seen switch bounce? Do you know what that looks like? I'll show you a video here in just a minute. In fact, I think I've got it set up where I can just click this, and you'll see it. Let's see how well that works. I'm asking my computer to do a lot.
What we're looking at here is switch debounce. The switch is switching from a high state to a low state there. You can see it doesn't switch directly. It makes and breaks several times. That's what's known as switch bounce. In this case, the switch bounce is taking about 500 microseconds before it settles down, half a mil. Sometimes it'll take longer, sometimes less, and occasionally you can see that during a make, it doesn't affect it grossly. During the break, it seems to affect it more on this particular switch.
Quick video with an oscilloscope to show you switch bounce, where the switch is not just going from high to low, it goes high, low, high, low, high, low a bunch, and then settles. Anyway, that's a problem because the Arduino is actually fast enough to detect those high-low transitions, and to it looks like you've pressed the button multiple times. Okay, and if your code is trying to count button presses, you've got a problem, right? Sometimes it's a problem, sometimes it's not. There's many different ways to get around this. One way is with a circuitry. So here's your bouncy circuit with just a resistor. Here is a circuit that has what's known as a flip-flop. It's a memory device, basically. It uses NAND gates, which is not AND gates. Don't worry about that too much. I'll explain all that probably in more detail later. If you had controls with me, we looked at NAND gates. Okay, but essentially what happens is when the switch is made, the circuit remembers the very first make and maintains that make until it's been cleared. Okay, so you can actually get debounced circuits to put into your projects if you want. Another way to do it, there's actually a software solution. You can have, and I'll just show you the code. I won't show you what it does in detail, but on the Arduino site, you can make a little bit of code that basically does the same thing. It remembers. It notices the first make and then counts time, waiting for the switch to settle out, and so that's how it works. So, anyway, all interesting stuff. But you need to know that mechanical switch bounce exists. So that way, if you're pressing a button once and your code counts 100 makes and breaks, you know what's going on. You know you've got switch bounce and you need to deal with it. Okay. All right. So the blink program turns the LED on and off, and there's another program I wanted to demonstrate for you. I'll go into the IDE itself to show you this one. This is a fairly simple program. It's called Button, and we'll just go into the IDE. I didn't copy this into the slideshow. Thank you. I can't talk this morning. I haven't had my cup of Java, but I don't drink it, so I guess it doesn't help. All right, here's the core of the code. There's a few more instructions here, and I want to describe to you what these are doing. First of all, up here we've got declarations of variables. So we've got a constant value that is in... I'm sorry?
I wish our TV didn't cut off the first 3 letters.
Oh, thanks for reminding me. Hang on. We'll fix that. For Anderson students, we've got to display a large TV the students are looking at, and it doesn't show the left-hand side very well. Is that better?
Yep.
Get it where I can use as much real estate as possible. Okay, so this variable is called button pin. Okay, and you try to name your variables so that they make some sense. So what do you think this variable is? It's the pin number where the button's connected. Simple, right? That's all it is. And it doesn't matter. I mean, you've got a bunch of different inputs. No, you'll notice in the coding that 0 and 1 are not commonly used. The reason for that is because 0 and 1 are shared for the transmit and receive pins for the USB. So if you want to talk to the USB via the computer while a program is running, which is really useful for debugging, you can't use pins 0 and 1 because they're already taken up for the port. Okay, so it's something good to notice. So you usually start at pin 2. Usually use pins 0 and 1 open. Now if you need all the pins, of course you can use them, but you've got to disconnect the USB connector or you're going to get garbage. Anyway, so this is a constant value. In other words, I don't know why they declare it constant. You don't really have to. But anyway, it's an int, which means it's an integer. There's many different types of variables. Did you want to say something?
I was going to say, it's probably declared as a constant so it doesn't get changed anywhere in code accidentally.
Yeah, that's a good point because you don't want your button assignment to change. I'm a weird kind of guy, and I was in high school, and I wanted to program a game. I think I've told you guys I programmed a Tetris clone in assembly language. And the thought of self-modifying code really intrigued me at the time because you had the ability to write bytes into memory anywhere you wanted, even where the program was located. So the concept of self-modifying code is something that's really always grabbed my interest. So I guess my default has always been to let everything change that could change. So whatever reason. But yeah, you're right. It makes perfect sense for it to be a constant value and not change because we're not going to change the mechanical setup. All right, so do you guys know the difference between ints and floats and signed and unsigned? Sort of. They're just different types. It's basically just two things. How much memory you're going to set aside for the variable, because the bigger the number you want to store, the more memory it takes, and there's really not a whole lot of memory on this thing. Okay, you got to have enough memory for variables and for the code, and you run out fairly quickly. We probably won't run out in this class, but for decent-sized programs, it's pretty easy to run out of Arduino space. So you want the variables to be as small as possible and yet still useful. Okay, so an integer, if I remember right, I'll have to go back and look.
Integer's 4 bytes.
Is it 4 bytes or is it 1 byte?
Integer is
Because
4, short is 2, and byte is 1.
are you saying this from Arduino knowledge or from General C? See, it may be different in Arduino, and I don't remember. It should be in the reference. Let's see if we can find it quickly, because that's something worth knowing and being able to find. Search. That'll help. A lot of these details I don't try to memorize unless I'm really working a lot on that platform. I just go and look it up in a reference, and that's all I really expect you to do.
Table's probably at the bottom of the...
Yeah, let's see. That's what I'm looking for. I thought they had a table in the search results. It was going to be the most useful and quickest way to look at it. Well, I don't know if this is for... Yeah, Arduino variable types. Okay, so int on Uno Plus is signed. It's 2 bytes, so 16 bits. Minimum value negative 32,768, maximum 32,767. You guys remember from binary how the number of bits you have determine the maximum count that you can have? Okay, so if you have 16 bits, you can have 65535 different numbers. It's just 2 to the 16th power. Okay, and one of those numbers is 0, so it's 0 to 65535, which is 65536 different numbers. Okay. So that it's 2 bytes makes perfect sense. And a byte is 8 bits, by the way, if you don't know. Go ahead.
I was going to say, int on is on 2 bits.
Yeah, so it depends on the particular model of Arduino that we're dealing with. Yeah. Let's see. So this just gives you an idea of how much space in memory each type takes up, and then what the maximum and minimum numbers are for each of those types. So something worth knowing where to find. All right. So that's an int. So what would the maximum and minimum numbers be that button pin could take on? It's on the Uno.
1000 something.
Right, so we could have negative pin numbers if we wanted to, right? Negative 32,768 or positive 32,767. Okay? We don't have near that many pins, so I don't know why they didn't just make this a byte, because that would be more efficient, but whatever. There may be a reason it doesn't work. I don't recall. But I would try a byte size because the pin numbers go from 0 to, what, 13? So that's about it as far as the I/O pins go. Same thing here, constant int LED pin, so that's where our output's going to be connected to. And of course we'll have to have a current limiting resistor there. We'd probably need a debounce resistor or pull up or pull down, not debounce, excuse me, a pull up or pull down resistor on the button pin, because again it's probably going to be a single pole, single throw. Variables that will change, button state. So the button state would go from on to off or off to on. Okay. Now, what does this code do? Do you remember? How many times does this code run? Once. The setup function only runs once. So you can think of it as basically just going through the code line by line until you finally get to loop, and loop just keeps going through over and over again. Okay. Initialize the LED pin as an output. Okay, so pin mode, we want LED pin, which is pin number 13, to be an output, which makes perfect sense because that's the pin where the LED is connected. So it needs to be an output, not an input. Pin mode, button pin as input. Okay, notice how they're using the name, the variable name, rather than the number itself. This is good practice. The reason it's good practice is later on you might say, you know what, I can't use pin 2 for some reason, I got to use pin 4. No problem. You do it up here in the declaration of the variable instead of trying to find everywhere that you referenced pin 4 in the code. What I would do instead, I would actually do a declaration so that the compiler recognizes it and does not bother using any variable space. So I would define button pin as 4, and I'll show you, or 2 or whatever I want it to be, but I'll show you how to do that later. Okay, and it would use no variable space. Okay, so then we get into the loop, now into the meat of the code. So we set button state, which is a variable, equal to whatever we get from digital read of button pin. Notice digital read is not just a command, it's a function, right? We give that function something. We give it button pin. In other words, we give it 2 so that it knows which pin to go out and look at. Okay? When we say equals, what we're doing is saying digital read is going to return something. It's going to go get something. And we want it to put that something into the variable button state. So it'll either return a 0 or a 1. It is not a function that is void. Okay? It doesn't return nothing, it returns something. And it returns a 0 or a 1, indicating the button state. Okay? So digital read reads the button pin that we tell it to read, or whatever pin we tell it to read, and then returns whether that pin is on or off, high or low. Okay? That's what it does. Now, if you need to use a button input to some program I have you make, which you will pretty soon, here's the command you'll have to use. Straightforward. You can see how to use it by just looking at this sample code. Okay, so check if the push button is pressed. If it is, the button state is high. So here's our first conditional statement. This is an if-else structure. Okay, really it's called an if-then. We just don't have a then statement in this language. Okay, if this logical expression is true, then do this. Else, in other words, if this logical statement is not true, then do this instead. Does that make sense? Pretty straightforward conditional statement. So what is this logic comparison? Does anyone know what that double equal sign means?
It is comparative.
It's a comparison. That's right. It says if button state is the same thing as high, because remember we got button state from reading the pin. It's either high or it's low. If it's high, the button's pressed. If it's low, the button's not pressed. Right? So if the button's pressed, then we're going to turn on the LED. If the button is not pressed, that's the only other possibility, then we're going to turn off the LED. This is a pretty disappointing program. Basically, you hold down the button, the light comes on, you let it go, the light goes off, and you go, why the heck are we using an Arduino for this? Couldn't we just wire the button in series with the light? We could. Sure, that would work. But the reason we don't is because we can do more complicated things. In fact, when you come back from the break, which I'll let you go to in just a minute, I'm going to make a program that will toggle the LED state every time you press the button. You can't do that with circuitry very easy. Okay, it's possible, but it's much easier to do it on the Arduino because you can program the Arduino. So we'll press the button, lights will go on and stay on even when we release the button. We'll press the button again, the lights will go off. Does that make sense? So that's what we're going to do. Why don't we take our break? When you come back, I will have hopefully figured out what's going on with this Arduino, and then I'll be able to demonstrate some of the